Welcome! This is Derek Hengeveld here to talk to you about Veritrek and how it can help you unlock the power of your ROM. Veritrek is a reduced order modeling, or ROM tool, built for thermal desktop. What it does is it takes your existing thermal desktop models, reduces those down into a surrogate form, and then allows you to explore that surrogate model. In doing so, we can enable near real-time simulation results. Here we're going to have a simple example of the Veritrek Exploration tool, which shows some of that speed. What we're going to see are changes in input factors in this middle pane, and then the output responses over here in this 3D plot changing in near real time. So here we have a user changing input factors. These can be things such as symbols in your thermal desktop model. And on the right-hand side, we see the plot, again, changing in near real time in response to those input factor changes. So Veritrek enables faster, more effective exploration of your data by leveraging the power of reduced order models. It enables near real-time results. Its intuitive user interface encourages collaboration. You don't need to be an expert thermal desktop user to access the power of this tool. And finally, it provides more effective data exploration through advanced analysis capabilities. Some of these include screening analyses, factor sweeps, surface plots, point analyses, and optimization studies. The advantages of Veritrek are numerous. First, it provides reduced costs by enabling or leveraging the near real-time results. We have improved schedules through faster analyses, and just reduced costs by reducing the amount of time it takes to get to a solution. Speaking of solutions, by more effectively exploring a design space, we can get to more optimized designs by leveraging this tool. Again, I just want to reiterate that this is a tool currently built for thermal desktop. It relates input factors such as power, thermal conductivity, or optical properties such as emissivity to output responses such as temperature or hydraulic power. And finally, just to reemphasize, we can obtain thousands of simulation results in just a few seconds. So what is a reduced order model? It's an accurate surrogate of a high fidelity or thermal desktop model. How we achieve this is by using intelligent sampling and then data fitting. Our sampling methods are based on Latin hypercubes, and data fitting is based on Gaussian process methods. But how do we obtain a ROM? Well, what you would start with is a high-resolution model, again, a thermal desktop model, that would then be provided to LoadPath, our parent company, and LoadPath would then convert your thermal desktop model into a reduced order form. That reduced order model would then be provided back to you along with the Veritrek Exploration tool, which gives you the power to explore that reduced order model. So how is this different than a traditional modeling method? Well, in a traditional modeling method, one simulation takes 1 unit of time. For example, one simulation might take 10 minutes, or it could take 30 minutes. It's a linear relationship. 1,000 simulations take 1,000 units of time. We see this with the red line here. With the Veritrek approach, though, it's a little bit different. It's more of a stepped response. We have to pay a penalty up front in the ROM creation, where we're not obtaining any necessarily useful simulation results, although they are being used to create the reduced order model. But once that penalty has been paid, we then get a near vertical line that relates number of simulations to time. So let's talk about our sampling and data fitting approach for the ROM creation process. This is a very simple example that will hopefully demonstrate the two fundamental components to our ROM creation. On the left, we have our fundamental high fidelity thermal desktop model. This screenshot should look somewhat familiar to you as a thermal desktop user. Let's say in this particular model, we want to relate some input factor, let's say power, to some output response, let's say temperature. One thing we could do is we could run this model at a number of different input factor settings. In this case, we're running it at power values of 0, 1, all the way up to 5 watts of power. And what we're doing is then tracking a particular temperature response. Well, we've done that, and we have 6 different data points. The next step is that we would want to fit a line through those data points. Well, it looks fairly linear, so let's put a linear fit to that data. We come up with an equation, y equals 10x plus 10. All right, so someone might ask, well, what happens with an input power of 3.5 watts? Well, there's 2 things you could do. One, you could go back to the existing thermal desktop model. You could put a power value of 3.5 into that and wait for the simulation to run and track the output response, and you'd find that you would have a temperature of 45. The other thing you could do is you could simply put 3.5 into the model or the equation that we've developed, and you can more quickly come to the answer. Well, that's essentially what we're doing. We're sampling, we're collecting some data, and then we're doing a data fit to generate a reduced order model or a closed form equation of that data. But there's some very important differences between this very simple model and what we do in Veritrek. The first is that we're dealing with multiple input factors. In this case, we only had 1, but with some of the models that we've developed, we've used 10, 11, even up to 12 different input factors. Second, we can also track multiple output responses, not just one. And there's 2 really critical components that haven't been talked about yet. The first is, how do we select the number of samples, and how do we select where those samples are located? Well, that's going to be talked about in the next slide. And finally, the model shape is going to be unknown. In this simple example, it was very clear it was a linear fit of the data, but that's not going to be known ahead of time. So let's talk about these 2 things, sampling and data fitting. As I mentioned before, we use Latin hypercube sampling in Veritrek. It's a method for efficiently filling a design space. What happens is we take the range of each input factor and divide it into n intervals, where n is the number of samples. So let's take a look at 2 simple cases here. We have 2 input factors, x1 and x2, and we have n equals 4 samples that we want to place in our design space. So the first thing we do is we divide each input factor into 4 intervals, which we see here. We have 4 columns and 4 rows. And then what we need to do is place our 4 sampling points such that they don't share a row or column with another sampling point. So this first example here, we see we have a valid Latin hypercube sample in that each data point does not share a row or a column with another. But in this particular example, we notice that in the top left and the lower right corner, we don't do a very good job of filling the data space. So we take it one step further and optimize the Latin hypercube such that we maximize the minimum distance between points. What this does is it helps spread out the 4 points in this case such that we can better fill our design space. And that's what we see on the right-hand side. Again, each of these data points doesn't share a row or a column with another, but it more effectively or more efficiently fills the entire data space. The other critical component to what we do is the data fitting method, and here we use Gaussian process models. The advantage of Gaussian process models is it doesn't impose a specific model structure. For example, we don't need to know if it's a linear or cubic fit. The Gaussian process takes care of that for us. One of the advantages of the Gaussian process model is it fits the data, the sample data, perfectly. And that's great for computer experiments. Once we generate our training data, which are the results of our sampled runs, we then fit that data with Gaussian process modeling approaches. One of the critical components of this, though, is optimizing the hyperparameters within this model. Now, without going into too much detail, these two images show the difference as we change a hyperparameter, in this case L, from 0.4 to 4. On the example on the left, we can see that the model that was generated, this blue line, doesn't seem to do a very good job of fitting the data. We'd actually expect a linear fit. But as we change that hyperparameter from 0.4 to 4, it does a very good job of fitting the data. Veritrek has a pretty long history. This work was started back in 2009. And since then, we've done work with the Department of Defense, with NASA, and we're currently reaching out and working with some commercial customers. This next year and beyond, we'll be at different conferences like the Spacecraft Thermal Control Workshop, TFAS, and ICES to talk about this tool and hopefully reach out to potential customers. So from here on out, we're going to talk about the exploration tool. This assumes that a reduced order model has been developed and it's available. Now, the exploration tool allows you to interrogate that reduced order model and generate results very quickly. So the first video that I'm going to show is a broad overview of the exploration tool. There's three main components that you should be aware of. The first is this session pane. The second is this input factor pane. And the third is this output response pane. We've seen the input factor pane and the output response pane. What this video is really going to focus on is this session management pane. We're going to see how we manage our different analyses. So let's take a look. The first level are what we call sessions. And here we have a first session, which is based on a CubeSat reduced order model. Now we're going to go to another session, which is tied to a HexBus reduced order model. And finally, we have another session tied to a thermal model. Now let's go back to the CubeSat model. One level deeper, we can now go into our different analyses. This first one that we're seeing is a point analysis. The second one is a factor sweep analysis. The third one is what we call our screening analysis. We're now going to move into an optimization analysis. And our final analysis type is a surface plot or 3D plotting analysis. And we've seen that before. Now within each analysis, we can have multiple runs. So we're going to go back to our factor sweep analysis. And in this case, we only have one run showing. We can only see one line on the right-hand side. As before, as we change our input factors, we can see the output response is changing in near real time. In this case, every time we move a slider, we're running 10 simulations. Well, what if we want to have two different analyses run at the same time? For example, we might want to have a hot and a cold case run, and we want to see the differences between those two. Well, now we have two runs that allows us to look at that. Here we're adding a third run, and the user is going in and changing input factor settings for the third run. Again, we can see how quickly the results are changing. Right now, we're running 30 simulations every time a slider is being moved. We can see how fast it's being done. And let's move on to each of the individual analysis types. The first is the point analysis. This is probably our simplest analysis type. It's an Excel spreadsheet-like approach to relating input factors to output responses. As we saw in the previous video, to get there, we would simply select a session. We would add a new point analysis, add a new run. We would simply set the input factor values, and then in near real time, we would observe the results. So let's take a look at this video and kind of look at the point analysis in a little bit more detail. So here's our point analysis with one run. Again, we're changing input factor settings. We can see those input factor settings changing in our spreadsheet over here on the right-hand side. We're going to add a second run. We can see that being populated in our spreadsheet. and we can see the output response is changing as we change input factor settings. Now what we're going to do is we're going to add multiple runs very quickly through our import batch feature. What this does is this is a text file that contains input factor settings that allow us to import multiple runs very quickly. In this case, we imported 5 different runs. Those input factor settings were imported. Veritrek did the calculations very quickly. You probably didn't even notice how fast that happened. And now we're up to 7 different runs that are being evaluated with this point analysis feature. Here we're showing how we can change the input factor settings in the table itself. Let's move on to the next analysis type. This is our factor sweep. This essentially allows us to take a look at a single input factor and up to 2 output responses. So here we have an input factor, PCB power, and now we're going to change that to heat pipe thermal conductance. We're looking at that thermal conductance over a range of values and how that impacts a particular output response. In this case, it's a maximum component temperature. As we've seen before with this type of analyses, we can have multiple runs. Now we have 2 different runs. Again, a good example of this would be a hot and a cold case analysis. And now we're going to add a 3rd run. For each of these runs, we're running 10 different simulations across the range of input factor settings. So we're running 30 simulations every time we move a slider. Here we're going to show how we can have multiple output responses for a single input factor. So now we're looking both at maximum and minimum component temperatures against the range of heat pipe thermal conductance. The next analysis type is our surface plot analysis. This is an extension of our 2D factor sweep, where now we're taking a look at 2 input factors and a single output response. Here we're setting the different input factors. Here we have heat pipe thermal conductance and body-mounted radiator emissivity. Here we're going to show some of the graphical features specific to the 3D plotting analysis type. We have a top view. We're looking at a right view, and how we can zoom in and out. With each of these views, we can simply save or copy the image as a PNG or a JPEG. We can then export that or paste that into a report or a presentation. Here we're changing our input factor settings, just as we saw with the 2D factor sweep. As we move the sliders, the graph updates almost instantaneously. Our next analysis type is our screening analysis. What we're going to see here is the relative importance of input factors for a given output response. So let's take a quick look. We have 7 different input factors, and we want to determine which of those is most critical to a given output response. In this case, maximum component temperature. First thing we're doing is we're just getting rid of some of those input factors. Maybe they're not important to us, so we're deselecting those, and we're left with 4 input factors. And by just simply looking at the length of these bars, we can find out which one is most important, or which has the most importance on the output response, maximum temperature. Here we've added a second output response, minimum PCB component temperature, and also added a second run. Again, all of this is happening very quickly, and the results are updating in near real time. But this is a very computationally expensive process if you were to do this in a traditional sense, using high fidelity modeling approaches. Here we're changing the range of one of the input factors for the 3rd run that we've generated. And again, all of this is done very, very quickly. Our final analysis type is our optimization analysis. What this does is it verifies a final design's parameters are within the required design envelope. Essentially, it's a Monte Carlo approach where we take the range of input factors, the range of each of our input factors, and randomly select design points within that range and then plot the results for 2 different output responses. In this case, we're plotting maximum and minimum component temperatures on this graph. So let's take a look at that. All right, first thing we're going to do is we're going to add a new run. We've already generated some points on the right-hand side. We're going to deselect some of the input factors for this second run. Perhaps orbit wasn't of great importance for this particular analysis. We're going to add 100 points to run number 2, and we can see those results being plotted on the graph, those points in purple. We're adding a third run. Again, we're deselecting orbit. We're selecting a nominal value, in this case, cold case. We're changing the range on one of the input factors and adding points to the third run. We can see those points plotted in blue. Finally, we're adding another run number 4. We're going to change our orbit to a hot case, and we're going to add 100 points to run number 4. Now what we're going to do is we're going to add 500 points to each of the 4 runs. So we're doing 2,000 simulations. And there, we're done. Just in a few seconds, we just did thousands of simulations. So I'm going to end with just a few slides. The first one is just going to give an example of some use cases of where Veritrek could be used. Some of this is based on some of my past experience as a thermal modeler. Others are based on some feedback we've gotten from customers and some other representatives that we've worked with. So let's just take a look at this based on the engineering design process. This is probably something you're very familiar with. On the left-hand side, we're very early in the design process. On the right-hand side, this thing is ready to fly. So on the left-hand side, we might have some sort of evaluation of technology. Maybe you're looking at different technologies like heat pipes or high thermal conductivity materials. What we want to do is identify which of these is the best approach for your particular thermal design. Well, we could use the Veritrek screening analysis very simply, go in to identify which type of technology would provide the most bang for your buck. Another place where this could be used is based on an example I had from a past project where I was looking at a variety of insulation approaches and is trying to do some trades on insulation parameters such as emissivity, absorptivity, and E-star values, along with other design parameters such as power, orbits, things like that. What I found is I was just doing a lot of iterations where I was changing E and alpha values based on insulation vendor requirements, plugging those in to find out if they meet both hot and cold case requirements. Had I had the Veritrek tool, it would have been a much simpler, a much faster approach to get to my solution. Two examples that I think are maybe less obvious of using Veritrek include meeting reviews and report updates. Within a meeting review, I think we've all been there. You've probably been asked a question during some sort of design review, and the typical answer is, well, I'll get back to you. I'll go back, I'll run the thermal model, or I'll ask my thermal analyst to run the thermal model. We'll get back to you in a few days with the results. Well, with Veritrek, with the available reduced order model, we could provide those results during the meeting itself. Again, we can leverage the near real-time computational power of this tool. A couple other examples include working fluid evaluation. This is some of the work that I had done with the NASA folks. They were trying to look at a number of different working fluids for a very complex thermal model. And finally, heat pipe performance. Perhaps you get to the end of the design cycle and you may have a underperforming component such as a heat pipe, and you want to evaluate or quickly evaluate what's going on. And lastly, I'm going to leave with a very simple example that kind of talks about the power of Veritrek. Let's say you have a thermal model and you have 5 input factors, each at 5 levels. Well, that would take a little over 3,000 runs to fully evaluate that design space. Well, you can imagine how long that might take using a traditional approach where you're running 3,000 or a little over 3,000 cases. Well, with Veritrek, what you could do is you could take that model, you could reduce it into a reduced order model form. That process would only take a few hours, then use the exploration tool to operate on that ROM. And again, as we saw, we can run thousands of simulations in just a few seconds Once we get to our optimized design, we can then go back to Thermal Desktop or some sort of modeling program and verify that optimal design in just a few minutes. So that's at a high level, that's what Veritrek is. If you have any questions, feel free to visit us at www.veritrek.com or reach us at veritrek@loadpath.com. Thank you, and I look forward to hearing from you in the future.